Okay, at long last, here we go. This is the beginner track, as I mentioned. So what we're aiming to do with these sessions is to give everybody here an introduction to the wonderful world of C++. So these sessions, the Tuesday ones, I said this already, but they're kind of lecture style, kind of me at the front, talking, demonstrating, showing you things. I'll also mix in some class exercises, just because otherwise it's like 2 hours of me talking, and everybody's concentration wanders after 2 hours. You can't really be blamed for that. So I tend to mix in some exercises, just short little sort of 10, 15 minutes. Just after I've shown you something, I'll usually go and say, okay, now you go and have a go at this. Here's what I'd like you to do. And it just breaks up the session and lets everybody kind of refresh and chat amongst yourselves for a bit. Because otherwise it's a lot, like as I say, it's a long time to be kind of switched on and following things. With the best will in the world, we can't turn you all into expert programmers, right, in the space of a few short weeks. It would be lovely if we could, but it's just not really possible. So what we want to do is to try and give you enough information to get started, right? So to understand the concepts, to be able to write kind of simple programs yourself, to give you a grounding so that you can go on and learn the more involved stuff yourself, right? It's a bit like, it's like learn to play a musical instrument, right? If you want to learn to play the piano, so you start off playing, Twinkle Twinkle Little Star with one finger, and eventually you keep going, and then you're playing the minute waltz like blindfolded, and you're amazing. But it takes a while to get there. It needs practice. Practice is just as important for programming as it is for learning any other skill. Learning a musical instrument being a great example, right? So 2 hours a week, you're not going to become an expert piano player if you have one 2 hour lesson a week with 30 odd other people. But over time, if you have the lessons and you're doing the practice at home in the meantime, then you will improve. And then things will get easier. And then you'll start recognizing, being able to sight read music or whatever the skill is that you need. So what I'm trying to say with this is try and do some, if you have the time, and I appreciate not everybody does, but if you have the time, then if you can do some practice in your own time, and not today because this is like the very first session, but usually I will give you like a homework exercise, something to encourage, somewhere to go, somewhere to encourage a bit of further reading, to go a little bit beyond what we actually covered in that session. So I really encourage, if you've got the time, then please do go ahead and try those, because you'll find you advance much more quickly than, especially if we're now doing this fortnightly. It's a long time. You kind of forget what we did 2 weeks ago. So, yes. One IT problem after another time. That's still not right.
What's the resolution?
VGA, terrible. Oh, look at the screen and then look at. No, separate display.
One second, I'm just going to restart the stream and then bring it back up.
All right. I'm going to do this one very quickly because we're so behind with the time through various problems. Anyway, so we break things down into various modules. This is just a set of topics, basically, that run for sort of 4 to 8 sessions, usually about 6. We do that, and then we have a little sort of question, multiple choice thing at the end. Usually, it's more for us, so we can kind of know how people are doing, how they've understood the material. That does say gauge, not gouge, doesn't it? Anyway, yes. So this module is initial C++. As I say, we're not assuming that anybody has any sort of programming knowledge, C++ knowledge for this particular module. If you do have some programming experience, you're probably going to find most of what I say tonight, if I ever get around to saying it, you're probably going to know what I'm talking about already. It will help, but as I say, it's not required. The other thing to say, and this is what we were just trying to fix a second ago, is that we live stream all of our sessions to the big wide world on YouTube. So hello to anybody who's watching on YouTube. The URL is on the screen there, youtube.com/CPP London Uni. And YouTube is great because it live streams it out and then it saves all the recordings afterwards. So everybody can go back, and there are, I don't know, dozens of videos on there from our previous sessions. So if you can't make it for whatever reason, things come up, of course, then you can join us live, or you can watch the videos later at your convenience. And that's the best way to catch up if you miss a session. The slides I always forget, and somebody has to prod me and remind me. But when I remember, or when I get prodded, the slides go on our GitHub page. So github.com, again, github.com/CPP London Uni. You'll go there, you'll see it's divided into lots and lots of different repositories. If you just go to that page, you'll see a whole list of them. This one will be called something along the lines of Initial C++, January 2020. So as I say, I tend to put them up afterwards because having tried it both ways, I much prefer to have everybody's attention on the screen rather than on their own laptops looking ahead to what I'm going to say in 5 minutes' time. So I tend to put them on afterwards. But yes, they will go up. We do like to hear from everybody, the good and the bad, and by far the easiest way to talk to us and to talk to everybody else who's with us is to join the CPP Lang Slack. So for those who haven't heard of Slack, it's basically just a chat application. You can run it in a web browser, or you can download. There's like an app for phones and for computers and stuff. There's a Slack group which is called CPP Lang. That's for it's got probably, I think it's like 10,000 users on there, and it's like a worldwide thing that people use to discuss the C++ language, right? And this group consists of hundreds of individual rooms, and we kind of piggyback off. So we don't run this, but this is run by another organization in the States, but we kind of piggyback off it. We've got our own little chat room in there that's #CPP London Uni. So this is Absolutely free to join, but you do have to register. So you can go to that URL, slack.cpp.al, and it's got a little thing on there. You just pop your email address in. It'll send you an email just to confirm that you are who you are. You're not like a robot. So then you can join the CPP Lang Slack, and you can join our particular chat room in there, and then you can talk to us 24/7, day or night. Well, maybe not. Well, we might not respond. Let's put it that way at 3 in the morning, but you never know. We do keep funny hours. We are programmers after all. So, this course, this thing that we do, is about the programming language C++. So why C++? Why do people use C++? There are hundreds of programming languages out there. There are probably 10 or 12 of them that are really the heavyweight ones that are used really heavily in industry. They all have different pros and cons. So what is it about C++ that makes me like it and Ollie like it and make people want to learn it? Why do people use it? And the answer to that is usually because it's fast. That is, programs that are written in C++ generally execute really quickly compared to equivalent programs written in other languages. Not always, and it depends on the skill of the programmer to some extent. But it offers facilities that allow for fast programs that other languages don't necessarily provide. We can have direct access to hardware. This is the really kind of low level, like messing about with the raw like bits and bytes of your memory. We have these things that we call zero overhead abstractions. So this is kind of nicer ways of doing things that is still doing that raw, like poking at bits and bytes under the surface, but doing it in a way that is easier to program, harder to make mistakes, makes life a lot nicer. But in the end, when you compile your program, all of that disappears, and it's just as fast as if you'd done all the ugly stuff yourself. This is in particular what makes C++ so powerful, and why it's used for these applications that want like really fast performance. And the other thing is efficient resource usage. So not only do things execute quickly, but in general, they don't use any more memory than they have to, right? It's very memory efficient. We have this system that I'll talk about in a few weeks down the line that allows you to release resources as soon as you have finished with them. You don't have to wait around for something to be deleted in a few seconds' time. Once you're finished with it, it's gone. And that's, again, one of the things that makes C++ very attractive to people. And C++ is used everywhere, including in a lot of places you might not even imagine. Used on things you might not even consider are computers, right? I don't know, like, say a microwave oven. You don't think of that as a computer, but it probably does have a little chip in there that's, turning the power on and off, that's counting down the little timer. There's a good chance that's running C++, right? Which is kind of crazy. But again, that comes down to this efficient resource usage. The fewer resources you can use, the cheaper you can make your microwave. At the other end of the scale, C++ is used on like the world's most powerful supercomputers, these absolute behemoths that run in these data centers, in wherever. It's the whole gamut from the tiny things that, again, as I say, you might not even consider as being a computer, right up to the world's most powerful things. In particular, C++ is used, it's ubiquitous in the games industry. Pretty much every PlayStation or Xbox or whatever game that you've ever played has been written in C++. It's used very heavily in the financial industry, in banking, trading, all of those sorts of things, they really like C++. It's also used, your laptops that is sitting in front of you, if you probably have a browser open right now, and that browser is written in C++. Right? It's very, very flexible language. C++ is brilliant, and everybody should use it for everything all of the time. Right? I mean, why do other programming languages even exist? Well, this is where I sort of have to come clean with you. There are perhaps some downsides. And one of the downsides that people frequently point to is that C++ is hard, or it's considered hard, or it has a reputation for being difficult to use. Well, this is sort of true, in a way, kind of. Because we have these low-level facilities, like things like pointers and memory management that you can optionally do if you need that absolute last 1% of performance. And it has a lot of features. Other languages are smaller, they don't do all of the things that C++ can do. So if you want to know the entirety of the language, that's quite a tall order. But you don't have to know the entirety of the language in order to be able to do useful things with it. The other thing is that, as I mentioned, C++ has been around for a very long time. It's one of the oldest programming languages that's still in mainstream use. And there are a few things that, they seemed like a good idea in 1983, but turned out not to be such a great idea, but we're kind of stuck with them now. But again, they are generally trying to phase these things out as time goes on. So I don't think it's that hard. I am confident that everybody in this room can learn the basics of C++, and once they've got the basics in place, then they can go on and gradually gather up the knowledge about the rest of the language as well. Right? It's not that hard. It has a reputation, but it's like a big scary dog. Once you get to know it, it's actually just really loving. Really just wants to help you. Right? Don't be afraid of its teeth. It wants to love you, really. The analogy of C++ as a fearsome dog, I think has probably never been done before, so there you are. Yeah. I'm going to skip over this slide because it's not immediately relevant to today. It's just for a bit of background knowledge, but we're a bit behind. But this one is important. So C++ is nowadays evolving quite fast. They release a new version of the standard every 3 years. So we had 11, C++ 11. That was the update that was introduced in 2011. C++ 14 was another update after that. Then we had 17. At some point this year, we will have 20. Then there will be 23, 26, 29, 30, etc. Right? That's the plan, at least. In particular, the C++ 11 update, as it's known, that was the version that was released in 2011. It changed the C++ language dramatically, modernized it dramatically, to the extent that old C++ code using this previous standard is really pretty out of date now. So unfortunately, there is still an awful lot of material on the internet and a lot of textbooks in libraries and things that date from before 2011. So while we very strongly encourage you to go ahead, do your own reading, use whatever resources you have available, textbooks, websites, whatever, make sure that they're teaching you stuff that's actually useful. That's the 2011 version, C++ 11, right? There's no point learning C++ 98, the previous version, anymore, right? So C++ 11 is what you want. And I am sorry that time pressures are meaning I'm zapping through this at 90 miles an hour. But this is just like the introductory the introductory background stuff. This is not the meat of what I was intending to talk about today. But let's all have a go at writing something. So if anybody is not connected to the internet, pop your hand up and I'll help you out. But for those of you who are, I'd like you please in your web browsers to go to this URL, onebox.org. If it's the first time you've been on there, the text box will have some stuff in, actually some stuff that looks almost exactly the same as that, but never mind that. You can just delete that and just type in what is in that little box. And then you'll see there's a button on the website. You can click run. And it will run this little program. And then we'll have a bit of a chat about it afterwards. No, it works, and it works for a couple of minutes and then cuts out. Okay, well, he's got lost on the way to the water cooler, so never mind. Who can tell me what that program does that you just typed in?
Have a guess. Let me try. And maybe bring it back up so I can try and pick it.
Well, it should be on the screen, right? But who can tell me what happens when you click run? It said something like start, and then finish at the bottom, and in the middle it said hello world. Right. The purpose of this program, the entire purpose, is that it prints hello world. And then it puts a new line at the end as well. That's it. This is not a very interesting program, right? But it is traditionally the first program that anybody ever writes in any new programming language, right? There's even a Wikipedia entry for hello world, right? It's ubiquitous, it's traditional, we have to follow tradition. This is the first program that you must write. It's like the law, right? So now you've all done that. Now you have taken your first step on your C++ journey. So congratulations to everybody. Don't worry, I'm not expecting you to know what those mysterious characters do right now, right? All will become clear. Hopefully some of it will be a bit more clear by the end of today. But then after a few sessions, you'll be able to look at that and you'll be able to look at each of those lines and you'll be able to know what that is doing. That's the idea. But really, not only was it just to get you to write some C++, but I also wanted to just give you a taste of what C++ source code looks like. And well, it's not on the screen anymore, but it's probably still on the computer in front of you. And as I say, things will become clearer as the course progresses. So a couple of things that are worth mentioning right off the bat is that if you have done any programming before, I know one of two of you put your hand up, you might have used languages like Python and like JavaScript that are what we call interpreted languages. Whereas C++ is what we call a compiled language. Yeah.
Same thing. Sorry. Well, what is a compiler then? You want to know that one?
Turns into ones and zeros, what you've written.
Spot on. Yep. So C++ is what we call a compiled language. So what this means is that you write your source code, you write text. Text just like you wrote just now in that box on the web page. You write a text file. That's what we call your source code. These are these, funny symbols, squiggly brackets, and all of those things. And then there is a program, usually installed on your computer, that reads this text file, processes it, and turns it into, as you said, ones and zeros, turns it into an executable program that you can run on your computer. So I'm sorry, just to the nature of the thing, I am going to be throwing quite a lot of terminology at you tonight. It's unfortunate, but it's just kind of the way it has to be done. But if I do say anything that's not clear or you're not quite sure what I mean, then please do raise your hand, because if you have a question and you're sitting there scratching your head, the chances are other people in the room also have questions and they're too shy to put their hand up. So you should be the brave one and you should ask the questions. But yes, a compiler is a program that takes your source code and translates it into a program that your computer can run. And this is, not all programming languages work this way, but C++ is one that does. And what this means is that many potential errors in your program can be caught by the compiler. So the idea is you write your program, you compile it once, and then it gets run a million times because you've deployed it to a million users, right? So the earlier you can catch errors, the better. It's better to have the error come up once for the programmer than it is for it to come up a million times for each user, and then IT support goes crazy because everyone's reporting they're getting this error message pop up, right? It's much better if we can catch the errors as soon as possible, or potential errors. So we have this program. It's a program that makes programs, a compiler. It takes your source code, produces the output, produces the program as an output, and then you can go ahead and run that program that the compiler has created. So it's like a two-step process, right? OneBox, the website that we've just used, kind of hides all this for you, right? OneBox is actually doing this two-step process behind the scenes. It's reading the code that you input, it's sending it to the compiler, creating the executable, and then running that. So it's kind of hiding this two-step process, but that is what is happening behind the scenes. But when you do this, if you do this on your own computers later, as you will do in a week or two, at least 2 weeks, you'll see that you do have to do both of these steps. You do the compilation, and then you run. Yeah.
That does also imply, not just apply to me, and I can't remember who had this quote. It's a wonderful quote. It might have been Dystro. Code, whether it's C++ or anything else, is written primarily for humans to read and understand, only incidentally to be converted into something for the computer to actually run. When you're writing C++, it's really for you and other people to read and understand. The computer just converts it, doesn't care.
So what's happening is that we have your source code, your text, and it is literally just a text file. We usually give it a different extension, .cpp, so that it opens in an editor rather than just like Notepad. But we have your source file. The compiler does stuff with it, reads it, understands it, gives you any error messages if you've made any mistakes. A couple of you had that. You had typos when you would have seen printed out in red, said, "Oh, I don't understand what this thing means." But if it reads it successfully, then it will go ahead and it will generate what we call an executable. That is a program that you can execute, that you can run. And we'll see this diagram again in a couple of minutes. The other thing to note, if you still have that program on the screen in front of you, you'll notice the very first line is this. It's 2 forward slashes, followed by our first C++ program. Right, so this is what we call a comment. Comments are purely for information of programmers reading the source code. Right? Comments are completely ignored by the compiler. So all programming languages have some ways of doing comments, some way of doing comments. In C++, you start a line with these 2 slashes, and then everything up to the end of that line is just completely ignored. So that's for like single line comments, like this one is. There is another way of writing comments as well. Again, this isn't common if you've ever done, for the few people who said they had some background in this, if you've done some JavaScript or Java or C# or whatever, a lot of them follow the same scheme. Another way of writing longer multi-line comments is that you start with a slash and a star, write your multiple lines of text, and then you end with the reverse, so you end with star slash. And everything that appears between those characters is ignored by the compiler, is purely for the information of the next person reading the code. And the other thing you might have noticed in that program is that there are a lot of these things. Semicolons. I think there are actually just 2 in that program, but in general, most statements, there's most lines of C++ that you write, end with a semicolon. Exactly as this one does. You can think of a semicolon like this as being like the full stop at the end of a sentence. And forgetting to type the semicolon is like the #1 easiest mistake to make. Right? I still do it several times a day. It's it's very, very, very easy to do. Fortunately, when you do, and then you ask the compiler to read your code, most of the time it will say to you, I think you meant to put a semicolon there. And you'll look at it and go, oh, yeah, I did. 99% of the time, if you forget to put the semicolon in, the compiler will tell you, it will say, you forgot. And you'll go, yes, okay. Very occasionally, it's possible that, a bit like in English, if you don't put a full stop in, it's possible that you could have 2 sentences that kind of run together that make something that's sort of grammatical, but not really what you meant. Punctuation can change the meaning of a sentence. And it's a bit like that. Very occasionally, you can forget a semicolon and the result turns out to be something valid, but kind of doesn't make any sense, doesn't do what you intended to. So sometimes you can see strange errors, strange results, and the #1 first thing you do is you go and look and make sure all the semicolons are where they're supposed to be. Right? I cannot tell you how easy it is to forget to do this. As I say, I've done C++ for like 15 years, and I forget it all the time, every day. So, yes, you will probably forget, but 99% of the time you will be reminded. If you don't get reminded and you get an error, first thing you do, make sure your semicolons are there. All right. Let's just put that little program to one side for a second. We will come back to it. But we'll put it to one side for a second and ponder a question, something perhaps a bit more philosophical than technical. And that question is this. What is the purpose of a computer program? It's a very general question. What is the purpose of a computer program? Yeah.
Obviously, we need to do certain tasks or bunch of tasks or
To perform a task, or some tasks,
or a system of tasks.
or perform a system of tasks. Yeah, that's good. Any advance on perform some tasks?
Or control something with these applications.
Control something? Maybe. I mean, some programs just display something, but
Working with information.
sorry. Automate something. I like that. Yeah, I mean, that was the kind of idea behind the very first computers, electronic computers. It's to automate processes that humans found tedious or made a lot of mistakes doing.
Another might be working with information, working on information.
Now we're talking. All right, working with information. Yes. I like the tasks and I like the information.
The most fundamental concept, right?
So I would say that in general, the purpose of the computer program is that we take some input of some form, we do some stuff, and then we produce output of some form.
Does that make sense to everyone?
We have some inputs, we transform that input in some way, and we produce some output.
So again, takes user input.
Hang on, well, right?
It's like using Excel.
Like using Excel.
Like you put something in the column.
So I went for the example of Word rather than Excel, but of course the same applies. You know, you're sitting there, you're typing, you're using the mouse as well, but that I didn't put that in. But you know, you're typing in Microsoft Word, or other word processors are available. Nobody uses them, but they're available. And then eventually you hit the right keyboard shortcut, and your printer beeps on the other side of the room, and out comes your essay on some nice crisp A4. Nobody prints things out anymore, I know, but still, hypothetically. We have inputs, we have a computer program, and we have some outputs. In fact, we've already seen an example of a computer program doing exactly that. It was a couple of slides ago. We have this computer program called a compiler that takes some input, does some stuff, and produces another program as output. Example Ollie was just about to ruin. You think about a computer game, right? That is a computer program. It takes some inputs. This is you madly tapping on the controller. It does some stuff. It displays polygons on your TV. And yeah, we got dead aliens.
Or a dead player.
Well, yeah. Of course, in real life, we don't just have one input, right? We have multiple inputs, and we might have multiple outputs as well. So we can think about, a web browser that you, again, all have open on your laptops right now. This is taking a variety of inputs. You're getting mouse clicks from the users, or touches if you're using your phone. It's getting like HTML instructions from, or downloading it from some web server somewhere off in the cloud. It's processing those in some way. It's going to run some JavaScript and stuff as well. And then eventually it's going to display a page on screen. That's the output of this program. It's the web page rendered on your phone. That was a fancy transition, by the way. Did you like that? That took me ages. It was just anyway. We have this program that takes input, does some magic, and produces some outputs. This is what computer programs do in the most general sense. But what is the magic? What are they actually doing behind the scenes, under the surface? A computer program is only just a list of instructions for the computer to execute. That is all it is, right? A list of instructions. All, only. And what we do is we write these instructions, in our case in C++, and we use the compiler to translate these instructions into machine code instructions. These are instructions that your CPU, the central chip in your computer, translates these into instructions that the CPU understands. And in complicated programs, things like web browsers, there are going to be billions upon billions of these instructions. Because web browsers are millions and millions of lines of C++, and these get translated into billions of lines of CPU instructions. Right? So it's just a list of instructions, but that's sort of conceptually easy to understand, but actually writing that is a complicated thing. We can't just write a list of 10 million things in one big text file. How do we manage all this complexity of handling multiple inputs, of rendering a page nicely, of running remote JavaScript, all of that, all of these things that web browsers have to do? Well, how do we manage any complex task? one second. Any big task that you are given to do. So if you are a student here and you're told you need to write a dissertation that's 10,000 words, right? You probably didn't just sit there and start typing and hope that you reach the end 10,000 words later, right? What do you do instead? Okay, I appreciate not everyone is a law student, but in principle, given any large project, given any large task, what do you do? Break it down. You break it down into smaller problems. Research is good as well. But fundamentally, when we have any large task to do, we break it down into smaller tasks, right? If you are told you've got to write your thesis, your dissertation, well, you might break it down into chapters, and then you might break down each of those chapters into like sections. Then you might, depending on how well prepared, you might even break that down into each individual paragraph, some people like to do, right? And large programs, small programs, pretty much every program that you write that's much bigger than the hello world we just saw. We break our large programs down just like that. We break them down into subprograms. So rather than just having this almighty task that oh my God, where do I even begin? You start to break the problem down. You break it down, instead of having one program, you break it down into subprograms, also sometimes called subroutines. And what does a subprogram do? It's a subprogram because it does, abstractly at least, the same thing. It takes some input, it executes a list of instructions, and it produces some output. That's why it's called a subprogram. Is this making sense? Yeah? Good. And once we've broken down our big program into some general subprograms, we can break down those subprograms again into smaller subprograms, and so on. And keep on distilling the problem, breaking it down into smaller, more manageable subprograms, just as you would with any large task, really. And eventually we keep on with this process, and eventually, all being well, hopefully, we end up with a large number of these small subprograms, each of which is easy to understand, hopefully, easy for the next programmer to read and see what it does, easy to test. Again, this is the ideal. It doesn't always work out like this, but this is the ideal. We start off with the big high level, this is what we need to do. We start thinking of breaking it down into individual tasks, then we can break each one of those down into their components, and so on. Subprograms of subprograms of subprograms. But fundamentally, they're all following this exact same model that the overall parent program, if you like, is doing. Taking some input, doing some processing, producing some output. I mentioned I was going to throw a lot of terminology at you, and apologies for that. In C++, we don't refer to subprograms. They exist, but we call them functions. This is in common with most programming languages these days. Way back in the mists of time, like when they were first coming up with this field in like the 50s, they did call them subprograms. At some point, the terminology changed to calling them functions. So nowadays, these subprograms are called functions. But a C++ function does the thing we want it to do. It takes some input, it executes a list of instructions, and produces some output. In C++ in particular, every function has a name. Hopefully a meaningful name that tells you what the function does. And that's how we refer to that function. That's how we identify it. So a function has a name, inputs, outputs, and the list of instructions. These are 4 things a function must have. Well, conceptually at least, at the high level. And if we want to execute a subprogram, run a subprogram in the terminology, well, we need to give it the input that it's expecting. It goes away, it executes the instructions, and it comes back with the answer. Right? So the name, by the way, comes from mathematical functions, which are kind of like the abstraction of this. But effectively, we say, OK, I don't care. At some point, you kind of think of them almost as black boxes. You don't have to know exactly how this function, this subprogram is doing its stuff. You just need to know that you give it the input, it comes back with the answer. So in C++, again, the terminology is that if we want to execute a function, if we want it to compute something for us, this is referred to as calling a function. Okay, I'm not really sure why. I don't know where the terminology comes from, but that's the term that's used. So when I talk about calling a function, what I'm saying is, function, here's some input, do your job, give me the output. Make sense? All right. Every C++ program is composed of functions, subprograms, if you like, but we call them functions. Every C++ program is composed of functions. And in fact, even that little, what was it, like 4-line example program that I showed you, that had a function in it. It had a function in it that was called main. So main, a function called main, is very, very special, very, very important. It's the most important function in any C++ program. Because rather than being a subprogram, this is the main program, right? I said that subprograms we call functions. Well, one of them is not sub. One of them is the actual thing, the place you want to start, the very top level, top of the tree, from where everything else descends. And in C++, as in some other languages, that function is called main. So if you've still got it on your screen, you might be able to see there's something on there that says int main, and then some empty brackets, and then some curly braces with a couple of lines in there. Well, that's the main function, and we'll look at it again in just a second. But when we run our program, this is like the high level, like when your operating system starts the program going, what actually happens is that we start reading the instructions in the main function. And we execute those instructions, and when we reach the bottom, when we've run out of instructions, our program terminates, our program ends. The operating system kills any resources that it still had, and that's it, we're done, we're finished. So if you like to think about it in terms of programs which call subprograms, which call subprograms, which call subprograms, you can think of this as a sort of tree going down, starting at the high level and working your way down to these like little functions at the bottom, little subprograms. If not everybody likes to think of it or finds it intuitive that way, but for people who do, main is what's at the top of the tree. Main is where everything starts where everything goes, where that controls the life of the program. Other people find it easier to imagine main as a function that gets called by the operating system itself. And again, if people who prefer to think of this as functions calling functions, well, you can imagine, it's not quite exactly how it happens, but you can imagine main as a function that gets called by the operating system. So most of our functions are called, that is, most of our subprograms are run from parent subprograms, and so on. Well, one other way of thinking about this is that main is actually just a subprogram, and the thing that's invoking it is your computer's operating system itself. These are sort of two alternative ways of thinking of really the same thing, which is saying main is the most important function. Program called main, it's a function called main is where everything starts. And one thing to mention that unless you are somebody who spends a lot of time playing with the Unix command line, and in that case, God help you, but you may not realize that actually when you run a program, it always returns a status code back to the operating system. When it finishes, it returns a status code. And this is not something you ever really have to think about from a user perspective, because this is kind of like a back in the 1970s thing when or perhaps earlier, when they invented this stuff. They had this idea that every program would return to the operating system a status code, and that would be an easy way to see, did this program do what it was supposed to do? Did it execute successfully or not? Nowadays, they're not used because everyone uses Windows and whatever, but we still have this kind of legacy thing from the 70s that the main function, its output, or one of its outputs, is an integer, what we call return value, that it returns an integer status code that we give back to the operating system. And by convention, the value of 0 means everything was fine. Any other value means something went wrong, this program had a problem, whatever. Yeah.
Is that why there's a 0 after hello world?
That is exactly. So if you look at the output of one box, if it's still on the screen for you, you'll see it says something like start, hello world, and then it's got a 0. I think it's in green. I can't remember what color scheme it uses. But that is actually telling you the return value of the program. So actually, let's just have a bit of fun. If you want, if it's still on the screen, just change the line that says return 0. Change that to like return 3.
Yeah, try that. It's transform. What? I tried that and it said return 1.
Yeah. And that might give you a bit of an idea of how we start returning things from functions, how we output things from functions. So the really important takeaway is that our program is broken down into functions. One of these functions is really important, and it's called main, and every C++ program must have a main function, and main is where all the action begins. So let's have another look at Hello World. This was it. Well, we can ignore those first two lines for a moment. The first one, as we said, was just a comment that gets ignored anyway. This one we'll come to a bit later, what that's doing. But this section is the definition of our main program. Of our main function, sorry. And a function has 4 bits of information we need. Its name, the input it takes, the output it gives back, and the list of instructions that it needs to execute when it's called. Well, the list of instructions is typically the longest, and that goes in between these curly braces, top and bottom. We have an opening curly and a closing curly. And in between there, that is the list of instructions that comprises this function. That is what we are telling the computer to do. Well, this line is just a very weird way of printing something out to the console. You don't really have to worry too much about how that works for now, but that's its purpose. And then we have this line that says return 0. And this is an instruction that says, I want you to return the value 0 back to the caller of this function, which in our case was the operating system itself. So we're going to return the output of this function is going to be the value 0. And remember, just by convention, the value 0 means everything was A-OK. So, a function, 4 pieces of information about it: its name, the inputs, the output, and its instructions. The instructions appear between these curly braces. We refer to the instructions, another piece of terminology, that's called the body of the function. Right? That's the main meat of it, if you like. Oops, sorry. So any questions about that bit, about why we break things down and what a function is? Either I'm really explaining it really well or everyone's just got bored. I'm just going to assume it's the first one, right? No, please do. If you have any questions, now is the time. If you ever see one of these green slides, it's because that's, for me, a mental note to say that that's the end of that bit. But it's also a really good opportunity for you to go, oh, hang on, I didn't quite, can you just go back? Right? So, please do. Yeah.
Does C++ have many functions written into it? Like, for example, if you have mathematical operators, are they considered functions that you call?
That's an interesting question. Does strictly speaking, no. If you do something like 3 + 2, that's not technically a function. On the other hand, you can kind of imagine that it is, because it is possible to write things in such a way that that the plus operator would invoke a function. So yeah, you can imagine it like it's a function call. Although technically speaking, it's built into the system rather than being something that you've written. Does that make sense?
You can't do it either, so they say 3 + 6 is always going to be fine. But are you familiar with types, the type system?
As in data type?
Yeah.
Like data type, for example, if you're doing plus on your own data types, then you could override or implement what plus would do for those.
Okay, I see.
Okay. So let's take another brief diversion on our journey. And again, as I say, today's just an awful lot of me talking, and I'm sorry about that. But unfortunately, there's just some information we have to kind of get over before we can really get into writing our own stuff. And part of that information that is really important to get a really good understanding of. So this is like pretty crucial. This is really important, what I'm about to say over the next couple of slides. And that's about the notion of types. So a type is a way of giving meaning to some data. So your computer operates on ones and zeros, right? That's all it knows. You all knew that already, I'm sure, right? The RAM on your system, the memory, is just millions, billions of ones and zeros. Your hard drive is effectively just billions of ones and zeros, right? So how do I know what these ones and zeros mean? How do I know that, all right, these 32 binary numbers that you've given me, 32 binary digits, 32 bits, how do I know that those 32 ones and zeros represent the number 27 and they don't represent the number 9.428? They don't represent the word, whatever a four-letter word would be. We do this through the magic of types. And the type of some data tells us what it represents and what we can do with it. And types are really, really, really central and really important in C++. And sometimes people kind of struggle to get what I mean when I talk about types, but actually, even if you don't realize it, you are probably already familiar with this just from having used computers, for most of your life, probably, most of you, right? Because like I said, your hard drive is just ones and zeros. And yet, you are able to have files of different types. A Word document is just a bunch of ones and zeros, yet somehow you double-click it and Word opens and it displays your CV or whatever it is. You have an MP3 file that you double-click and it opens in whatever your MP3 player is, or a video file, or a PDF, or you have all these different file types that you're probably really familiar with, right? Well, under the hood, they're all just ones and zeros sitting on your hard drive. But your operating system associates a type with each of the files, and it uses that information to know which program to launch when you double-click on it. Right? So all the files sitting on your computer each have a type associated with them, or almost all of them. Sometimes it doesn't know, and it comes up with that little box to say, what do you want to, how do I open this? I don't recognize this kind of file. Right? So you're probably already familiar with the notion of type, even if you've never really thought about it before. Oh, it's fun being on this side. Because files on your file system have different types. PDFs, MP3s, JPEGs, whatever, right?
Audio, video.
Yeah, list hundreds of different file types if you like. And in exactly the same way as we need to know the type of some data, or we need to know the type of a file on your computer in order to do something useful with it, we need to know the type of some data in a C++ program to be able to do anything useful with it. For example, we can meaningfully multiply two numbers, two integers. We know how to multiply. But if we have, might be the exact same sequence of ones and zeros, but this time it represents a string, that is a sequence of characters, like a word or a sentence. Well, what does it mean to multiply like hello by goodbye? Like that's not an operation that makes sense. It makes sense to multiply 3 by 2. It doesn't make sense to multiply hello by goodbye. But hypothetically, those could be represented by the exact same sequence of ones and zeros. But by giving them different types, we know what operations we are allowed to do. We know what those bits mean. And actually, C++ has lots of commonly used types built into it that we can use in our programs. Right? And this is really good. And down the line, it also has lots of facilities to create your own new data types. Classes, structs, enumerations, right? All these fun things. We can create our own data types as well, but we'll be doing that way down the line. And for now, we're gonna concentrate on the types that C++ provides for us. So C++ is what's called statically typed. And what this means is that when we have a piece of data in our program, the type of that piece of data is fixed forever. It is determined when the program is compiled, that is when we build the program from our source code. The type of every piece of data is determined when the program is compiled, and it can never, ever change. Right? Again, I stress this because this is different to the way some other programming languages work. But C++ is pretty strict about its notion of types. Another way of saying it's pretty strict is saying that C++ has what's called type safety. That is, it will only let you perform operations that make sense. It will let you, if it knows that, okay, the type of this bit of data is that it's an integer, and the type of this bit of data is that it's an integer, then, okay, you can go ahead and multiply those, and that'll produce a new piece of data that's also an integer, right? Because 3 times 2 ints, yeah. But if I have a piece of data that's a string, sequence of characters, and I have another piece of data that's a string, well, I can't multiply those together, right? Like I say, that makes no sense. So if we try and do that, if I try and do hello times goodbye, well, the compiler is going to give me an error. My program will fail to compile. You literally print out, I don't know how to do times for these two things. And what this means is that many, many, many potential errors in our program are caught by the compiler before our program runs. This eliminates a large class of potential errors. It also means that in a lot of cases we have to be quite explicit about the types that we want to use. We have to mention them a lot, which, like more dynamic languages like Python, you don't have to do that. But well, in C++ we do. But the trade-off is that we get to catch a lot of errors. Like before we even run our program, we can like verify that there's a whole class of errors we're not going to make. There are ways around this. There are like escape hatches, things you can do that are kind of ugly. But avoid them if at all possible. Like it's a sign that you're probably doing something a bit dodgy. You have to be a bit careful about. Right? Think of this as the equivalent of like changing the file extension in Windows. Right? If you have a PDF and you change the extension to like .doc, the Windows is going to think it's a Word document, but it's not really, is it? It's still a PDF. So if you try and open that in Word, it's just going to, if it opens it at all, it's just going to give you garbage, right? What you're doing there is you're trying to fool Windows file type system. And C++ is the same. It tries really hard to force you to follow the rules. There are escape hatches, but if you do, well, you might get garbage, and if you do, it's on you. So don't use the escape hatches unless you know what you're doing, is what I'm trying to say with that. So this notion of type is all important. Every bit of data in our program has a type. And all the types that we use have names. Well, almost all. And as I mentioned, C++ actually provides us with several useful named types that are just built in there, ready for us to use. And probably the one that you'll use, or certainly you'll see most frequently in my examples, because it's nice and short and fits on slides, is this type that's called int. And this represents an integer, that is a whole number. 0, 1, 1, 2, 3, 4, 5, minus 5, 4, 3, 2, 1. Right. There's another data type which is called float. And this represents what we mathematically call a real number, that is something that's got a fractional part. Again, 3.142, 2.718, minus 123.456. So an integer is a whole number. A float, we won't go into why it's called float, but anyway, it's called float, and it represents something with a fractional part. My ears are highly attuned. I hear somebody, there's an intake of breath as if a question was going to come. No. Okay. You can, yes. Yeah. Because that's a meaningful operation, right? And what that will actually give you is another float. Because if you think about it, if you've got like a whole number and a fraction. No, you can do, so if you did like 1 plus 2.718, you're going to get what you expect, like 3.718. Yeah.
However, your computer appreciates
There's another type called bool. That's actually, you might think this is really stupid, but it turns out to be really, really, really useful. Because an int can have like millions of billions, in fact, different values. A float can have gajillion different values. A bool can only have one of two different values. It's either true or it's false. And you might think, like, that's just dumb. But actually, it turns out that this is really useful a lot of the time. Right? It's called bool because it's named after this mathematician from a couple hundred years ago who was named Boole, who came up with this whole idea of what's now called Boolean logic. Feel free to go and look that up on Wikipedia if you're interested with truth tables and logic gates and stuff. But this data type is called bool, and it's either true or it's false. There's the one that nobody can pronounce. And even I can never decide how to, is it car or is it char? Right? Like the English word would be char, but it's short for character. Yeah. So sometimes I'll say char, sometimes I'll say car, sometimes like Americans say car, which sounds horrible to me. But anyway, what this represents is a single character. So that's a letter, uppercase or lowercase, or a digit, not a number, but a digit, or some punctuation. There are a few punctuation symbols that are included in this set as well. Things like, question mark and exclamation mark and comma and full stop and stuff. Right, the set of characters represented here is what's called the ASCII set. ASCII stands for something or other. But if you want to look into this, you can just in fact, you can just type ASCII into Google and it will give you the whole list of the whole 127 different ASCII symbols that are available. But we'll see, you don't have to memorize those symbols or whatever. You can just type them directly into your source code, and we'll find out how to do that in a bit. But yes, the data type char or char represents a single character. Single letter. Were you going to? No?
So it'll be a single digit like a 1, 2, 3, but not a 23.
Exactly, yes. Yes. We don't, as humans, when we're communicating, tend to deal with single characters very much. I mean, I see like a teen who's really into like just sending angry emojis and you just exclamation mark one character. We tend to write, type, communicate in sentences, words and sentences. This is a whole bunch of characters, one after the other, right? The word hello is capital H, lower E, L, L, O. It's 5 characters. We call a sequence of characters a string. Again, I've already said string a couple of times tonight, but what I mean is a sequence of this char data type. And actually, this can be absolutely as long as you like, right? It can have 0 characters, it could have 1 billion characters. There's really no limit. For reasons that we will get into down the line, this has a bit of a funny name. Instead of just being string, it's got this std : thing at the front. People get quite annoyed about it, but you know, for now we can just think of it as part of the name. It's part of the type name. These ones are nice and short. This one has this std : string. So this represents a sequence of characters. There's another data type that's also really, really useful, and that's something we call a vector. And this represents a sequence of some other type. So we could have a vector of int, we could have a vector of float, a vector of bool, a vector of char. Right? It's in fact what's called a generic type, because it can hold any type we choose. But once we've chosen, everything that's within the vector, that's the whole sequence, must have the same type. We can't mix types. We can't have a float and a string and a bool.
How do you know that's the vector char or a string?
Because, as you're about to see, when we use some data, we have to write the name of the type that we're using. So we have to inform the compiler what types that we're using. So, but that's a very good observation that really there's very little difference between a vector of char and a string. They are, well, in fact, implemented as exactly the same thing. The difference is that string gives you a lot of extra like useful functionality that's specifically for dealing with like text that vector doesn't give you, because that's like a generic container. But fundamentally, in terms of how it works under the surface, there is really no difference between a vector of char and a string. Yeah.
If you're talking about like Unicode characters, Japanese kanji or whatnot.
Yeah, that's not char.
Yeah, how would you put that in?
So that's it's a very good question. Right, so C++ is rubbish at handling Unicode. Is the very short way of putting it. There are many efforts underway to fix this, but it's hard for reasons. For the beginner course, my strong recommendation is just let's pretend the rest of the world doesn't exist and everyone speaks like English and doesn't use accents and stuff. In the real world, there are libraries like code resources available that provide functions that can do this stuff for you. But you need to know a bit before you can go ahead and use those, right? So, That make sense? Yeah. Yes, unfortunately, because of its age, pretty much, C++ began in the United States in a world where, 127 characters were enough to email the guy at the next university, which is all it needed to do to begin with.
C, really.
Yes, and then C++ inherited it from C, yeah. Okay. So that was a little diversion to talk about types. And the reason I needed to talk about types is because we can't start writing functions until we understand what types are and what type names are. So this is an example of a function. It's a very simple function. What this function does, anybody want to make a guess at what this function does? Adds. What does it add? Okay, what are A and B? Yeah, see, it's not so hard, is it? Yeah, no, awesome. Yes. So remember, there are four important pieces of information we need about a function. We need its name, its input, its output, and the list of instructions that it executes. 4 pieces of information. And all 4 of these pieces of information are on the screen now. So this is a function that's called add.
That just means you wanted to add the 2 integers.
I can name the function whatever I like. There are only limitations is that it has to begin with a letter, can't begin with a number, has to begin with a letter, and it can't have any spaces in it. Right? But I could have named this like Frobnicate if I wanted to. But in general, you should try and name functions after what they do. So in this case, it adds stuff, so I called it add. So the name of this function is add. This function takes 2 pieces of input data. Now, the notion of type, really important. So whenever we write a function, we have to say, all right, what is the type of the input data that I'm expecting? Every piece of data in C++ has an associated type. In this case, the function add is expecting 2 items of input data. And in this case, they both have the same type. They both have the type int. With the name, add. We have the inputs, that is their types, their number and their types. Because in C++, we can have multiple pieces of input data. In this case, we've got 2, and they're both ints. Then we need to know about the output. In fact, really what we need to know is what is the output type of this function. And that actually goes first. So what this is saying, what this first line is saying is, okay, I have a function named add. It takes 2 inputs, both of which are ints, and it returns a value that is an int. So again, this notion of type, absolutely important, absolutely central, crucial. We end up writing type names all over the place. So we add an int, and the result is an int. I know it's back to front. It's just weird. I'm sorry. It's just the way it is. Right. So we have the name, the inputs go in brackets, and then the what we call the return type goes at the front. Or if you prefer to think of it left to right, return type, name, and then in these round brackets, we list the input data that we want to operate on. We say that this function returns a value of type int. So that's three of the important bits about the function. There's a fourth, the most important, is the actual list of instructions that we want this function to execute when somebody runs it, when somebody calls it. Well, in this case, there's only one instruction that we're telling it to do. And that's saying, I want you to add these two inputs that I got, A and B, calculate whatever their sum is, and then I want you to use that as the return value of from my function. So this bit between these curly braces, we call this, as I mentioned before, we call this the body of the function. So if you hear me referring to a function body, that's what I mean. I mean the list of instructions that this function actually executes. So here we've got another example of a function. Anybody tell me what the name of this function is? Sorry? Print float. Well, you could tell that because it was probably the only bit of text on the screen other than this cout thing. Yeah, the name of this function is print float. All right. How many pieces of input data does this function take? The call from the front was 1. But you've been coming to these before, right? So I was hoping for one of the newbies. This function takes one piece of input data, which is of type. You mouthed it, but yeah. It takes one piece of input data of type float.
Can I have a question?
Yeah.
Because of the void, it doesn't return anything.
Hang on. Okay. What is the return type of this function? Void. Yeah. Well, that's weird, isn't it? Because I just mentioned a load of useful types and I didn't mention that one. Well, there is a very special sort of non-type, I guess. Well, it is a type, but it's kind of not. It's almost like a sort of placeholder. This word void. And what this does, if you put it where you would normally expect the function return type to be, what this means is this function doesn't return a value. C++ functions can return, they can have as many pieces of input as you like, but they can only ever return 1 or 0 values. And if it returns 0 values, if it returns nothing, then we use this special like placeholder type called void. So void is a special type that means this function does not return a value. And again, the body of the function comprises just one instruction, this weird thing that we don't really worry about for now, but the end result is that the value f will be printed out on your console. This stands for console output, if you were at all curious. So that's how we write functions. But we're going to have to execute them as well. And unfortunately, I'm just out of time. So I'll run through this in 30 seconds, but then I'll come just so, you know, half of it is in. So I don't want to leave you hanging halfway through. But the way we call a function is we just write its name. So inside the body of another function, when we're writing the list of instructions, one of the instructions we can write is just the name of the function followed by its input data. This is a way of writing a float number, by the way. Put an F on the end. So we might call our print float function that we just saw. We'll provide it with its input data. It expects one piece of input. And then we'll have to put a semicolon on the end, like the full stop at the end of the sentence. And this will call the print float function. Alternatively, we can call the add function that we saw before, and we supply two integers. And this will say, okay, right, I'm going to go away and, how you like to think of it, run this subprogram, call this function, execute these instructions, and come back to you with the results, if any. That's mostly for people doing other languages. We won't worry about that for a sec. So last slide for tonight. So we had print float just now, just to change things up. This one is called print int, because I'm silly and I should have just used the same example, but here we are. This is print int. It's a function named print int. It takes one piece of input data. It has type int. And it returns nothing. It uses this special return type void. Then we have the same add function we saw just now. Takes two pieces of input data, returns an integer, and his name is add. And now we've got our magic main function. Well, now you can see main is a function that takes no input data and returns an integer. Things are beginning to uncloud themselves from that mysterious hello world random sequence of line noise characters that you saw earlier. Things are beginning to, just starting hopefully, to take shape, I hope. So now we have our magic main function, takes no input data, returns an int, but this is a function we have to have. This is where all the action starts. And what we're doing is we're executing the print int function, our subprogram here, with the value 3. But actually we can do kind of clever things as well. Because here we're nesting function calls. This is saying, okay, I want you to add 4 and 5, and then this function is going to give you back an integer. And then I want you to immediately send the result of that to this function. So if you were, and this would work, if you were to type all this into one box, what this is going to do is going to print out the number 3 on the console, on in the little output box. And then it's going to print the value 9, because it's first going to calculate 4 plus 5, and then it's going to send the result of that to this function. So, and then we return the value 0 from main just to say that our program ran successfully, everything was okay. Everything's hunky-dory. So this is quite a bit more complicated than we just saw in a little hello world, right? There's twice as much code. But if you think about breaking things down into subprograms, the way you would break down any large task into subtasks, break a program down into subprograms. Here, we have defined these two subprograms, printint and add. In C++, we don't call them subprograms, we call them functions. So we've defined two functions called printint and add. in C++. Types are all important. We need to know the type. We need to state, in most cases, the type of every piece of data we use. And in particular, when we're writing a function, we need to state what are the types that that function can operate on, or does operate on. In this case, everything's an int, except for this guy, who doesn't return a value, so we use this special word void. And with that, I'm way over time, but I'm sorry we started late, so sorry to keep you all. But I will leave you with just a little thing that you can take away and do at home. And apart from that, that is it. I'll leave this on the screen just as you file out. But that's it for this evening. As I mentioned at the beginning, we do tend to go out for a refreshment because it's the air conditioning here. It's really dry. You need a beverage afterwards. So everybody is welcome to come and join us at a local establishment. But apart from that, it's been a pleasure. Sorry that we had so many technical issues to start with. Hopefully you managed to get something out of it afterwards. And I really hope that I'll be able to see all of you back in a couple of weeks' time when, fingers crossed, things will work a lot more smoothly than they did tonight. Thank you so much for bearing with us. That's it for tonight. Cheers.